Energy is everywhere. It powers our homes, fuels our industries, drives our vehicles, and even keeps our bodies alive. But what exactly is energy? And how does it connect to the environment we live in? Welcome to this series on energy and environment, where we explore the science, systems, and sustainability of energy in our world. Energy is the ability to do work or cause change. Every movement, every process, every transformation around us involves energy. From a moving car to a growing plant, energy is constantly being transferred and transformed. Energy exists in many forms, but two of the most fundamental types of mechanical energy are potential and kinetic energy. Think of them as two sides of the same coin: the energy of what happened and the energy of what happening. Potential energy is stored energy, the energy an object has because of its position or configuration. Kinetic energy, on the other hand, is the energy of motion. Let's start with a classic example: a ball at the top of a hill. It possesses gravitational potential energy. This energy is stored because of its position within Earth's gravitational field. We can calculate it with the formula U equals m times g times h, where m is the object's mass, g is the acceleration due to gravity, and h is its height. For a half-kilogram ball resting 10 meters high, it holds approximately 49 joules of potential energy, ready to be unleashed. Once released, a transformation begins. As the ball rolls downward, its height decreases, so its potential energy converts into kinetic energy. The energy of position becomes the energy of motion. We calculate kinetic energy with the formula K equals 1/2 m times v squared, where m is mass and v is velocity. Notice the v is squared, meaning an object's speed has a dramatic impact on its kinetic energy. Doubling the speed quadruples the energy. In an ideal system, the total energy, potential plus kinetic, remains constant. But potential energy isn't just about height. Consider a compressed spring. By squeezing it, we do work and store energy within its structure. This is called elastic potential energy. Its formula is U sub s equals 1/2 k times x squared, where k is the spring's stiffness constant, and x is the distance it's compressed. The more you compress it, the more energy you store. When you let go, that stored elastic potential energy is rapidly converted into kinetic energy, causing the spring to expand and snap back to its original shape. This principle scales up to massive proportions. The vast amount of water stored behind a dam holds immense gravitational potential energy. When the floodgates open, this potential energy is converted into the kinetic energy of flowing water. This powerful flow spins turbines, transforming kinetic energy into mechanical energy, which a generator then converts into the electrical energy that powers our world. This constant interplay between potential and kinetic energy is a fundamental engine of change, driving processes both small and large across the universe. Energy behaves differently depending on the system. But what exactly is a system? In physics, it's any part of the universe we choose to study, separated from its surroundings by a boundary. We can classify systems based on what they exchange across this boundary. An open system, like a human body, exchanges both energy and matter with its environment. We consume food and release heat. A closed system, like our planet, exchanges energy with space, but for the most part, not matter, which makes our planet a closed system in terms of matter transfer. An isolated system exchanges neither, a theoretical ideal, like the universe itself. In mechanical systems, we often analyze the conversion of potential to kinetic energy. In biological systems, life is powered by a constant flow of chemical energy from food. In electrical systems, we use energy carriers like electricity to move power from a source, like a power plant, to our devices. This highlights a key distinction: energy sources versus energy carriers, and the critical role of energy storage. From chemical batteries to vast water reservoirs, holding immense potential energy. And in vast atmospheric systems, solar energy from an external source drives the complex dance of weather and climate. Across all these diverse systems, from a single cell to the entire planet, one fundamental principle holds true: Energy is constantly being transferred and transformed, flowing across boundaries and changing form, but never disappearing. Energy appears in many forms, which we can broadly categorize as either macroscopic or microscopic. Macroscopic forms, like the kinetic energy of a moving car or the gravitational potential energy of water behind a dam, are properties of the object as a whole. Microscopic forms relate to the internal structure of matter. Let's explore these. Thermal energy is the microscopic kinetic energy of atoms and molecules vibrating within a substance. We perceive it as heat. Different materials store this energy differently, a property described by their specific heat capacity. Electrical energy arises from the flow of electric charges, like electrons moving through a wire. The power it delivers is a product of voltage and current, and it can be transmitted as direct current, or DC, or alternating current, AC, which is how it reaches our homes. Chemical energy is stored in the bonds between atoms. When we burn fuel or digest food, these bonds break and rearrange, releasing that stored energy. And then there is nuclear energy, the immense energy stored within the nucleus of an atom. Governed by Einstein's famous equation, E equals mc squared, it reveals that a tiny amount of mass can be converted into a tremendous amount of energy, making it incredibly dense. The most profound insight is that these forms are not isolated. They are constantly being converted from one to another. This interchangeability is the engine of our world. Radiant energy from the sun is captured by plants through photosynthesis and converted into chemical energy. When we eat those plants, our bodies metabolize that chemical energy, converting it into the thermal energy that keeps us warm and the kinetic energy that allows us to move. This continuous transformation, from sunlight to food to human activity, is a perfect illustration of energy's dynamic and ever-changing nature. One of the most important principles in physics is the law of conservation of energy. Energy cannot be created or destroyed, only transformed from one form to another. When energy seems lost, it is simply converted into less useful forms, like heat. Energy efficiency measures how effectively energy is converted into useful work. A traditional bulb wastes most of its energy as heat, while an LED produces more light using less energy. Higher efficiency means less waste, lower costs, and reduced environmental impact. Energy production involves converting natural resources into usable forms. Burning fuels generates heat and electricity. Solar panels convert sunlight into power. Wind turbines transform motion into electricity. But every system comes with trade-offs, a topic we'll explore further. Energy is measured in different ways. Joules, the scientific unit, kilowatt-hours used in electricity bills, calories for food energy, BTUs for heating systems. For example, 1 kilowatt-hour is the energy used by a 1,000-watt device in 1 hour. Energy drives our world, from economies to everyday life, but it also shapes our environment. In Part 2, we'll explore energy production, environmental impacts, and the future of sustainable energy. Stay tuned. Please like and share the video, follow and subscribe to this channel for more useful content.